Welcome to the 13th lecture for the NPTEL course on computer system optimization for machine learning. As usual, we will give you a brief recap and then we will discuss about DNN accelerators. In the last class, we talked about different types of data reuse in DNN. Specifically, we mentioned that there are three types of data reuse: convolutional reuse, feature map reuse and filter reuse. Different reuse technique try to reuse different data. Like for an example, in convolutional reuse, there is reuse of activation and filter weights. In feature map reuse, there is a reuse of activation and so on and so forth. And then we also discussed that if all types of reuse is actually utilized, then the DRAM access in AlexNet can be reduced from 2896 million to 61 million. So remember, whenever we are executing the DNN, there are a lot of data going around, right? The weights are there, the activations are there. Activations mean the output of one layer which is becoming the input of another layer, right? So there are a lot of data going here and there, correct? Now whenever we have data, most likely the data has to be stored in the DRAM, because remember, the on chip storage is very less. The amount of on chip storage is typically very less. Now our primary goal, or the primary goal of different optimization technique is to reduce the DRAM access, and here we are saying that if hypothetically we can use all type of data, we can employ all type of data reuse, then the total DRAM access in AlexNet can be reduced from 2896 million to 61 million. That is the best and hypothetical case, right? And then we went on and discussed about different stationary data flows. Specifically, we discussed output stationary, weight stationary, input and input stationary data flow. We discussed how those data flow work, and then we also discussed the different hardware performance parameters for these three data flow architecture, or these three data flow structures. And then we saw that like again, if we want to build an accelerator, then this can be the minimum number of MAC, minimum number of weight read, input read, output read and output write. Of course, we might not be able to build that kind of accelerator, because again that is the best and hypothetical scenario, but then whenever we build an accelerator, these should be our target. Okay. Now today, or rather for probably next 2 or 3 lectures, we will discuss about DNN accelerators. Specifically, we will discuss about 4 early proposal of DNN accelerator. We will first discuss DianNao, then we will discuss DianNao, then DianNao. They are all coming from the same research group. They are same DianNao series, and after that we will discuss Iris. So don't worry, I mean I will not discuss all these 4 accelerators in this half an hour lecture, but in probably for next 3 lectures we will cover all the 4 accelerators, right? Now before going into the detail, let us discuss why do we even need accelerators, right? I mean we have CPUs, we have GPUs, right? But then why do we care about accelerator? Yes, we have CPUs, but then when you talk about DNN computation, there are few drawbacks of CPUs. The first drawback is CPU does not have much parallelism. So for an example, if we have like octa-core CPU with let us say 16 threads, then we can at max process like 16 things in parallel, right? We can launch 16 tasks in parallel at max, right? But then if you think about DNNs, there are lot of parallel multiplication can happen, lot of multiplications can happen in parallel, right? Because remember, there are lots of filters, there are lots of channels, all the multiplications can happen in parallel, and then they can get accumulated to produce the output feature map. So CPUs are not very good candidate to accelerate the DNN application, because there is less chance of parallelism. Now yes, GPUs are there. So here I want to spend some time talking about why GPUs came into the picture. See, GPU are graphics processing unit, right? But none of these DNN applications or DNN algorithms are graphics algorithm, correct? But then yeah, I agree. I mean GPU, whenever the GPU came into the picture, it actually came to accelerate the image processing or the video processing task. Many of you may play video game. If you want to play if you want to have a good experience while playing a video game, then your laptop or the computer system should have a good GPU, because remember whenever we play a video game, watch a video, watch a movie, etc., whenever there is some image processing or video processing task, then the image pixels are getting processed, right. There is some algorithm happening which is probably finding the edges in the image pixels or finding the finding some similarity in the image pixel, right. Now, in that case, like while we are doing that image processing and video processing, in many of those image processing algorithm, we can actually do parallel processing on each of the pixel or each of the patch of the image, right. So, that is why GPU came into the picture, so that there will be single instruction, and then in the single instruction there will be multiple tasks launched. Okay. So, that is the basic of GPU. Of course, I mean there are too many details of GPU itself. Now, when this DNN algorithms came, or in general this machine learning algorithms came, it was seen that, I mean as we also discussed, right, there are too many parallel tasks, right, and then mostly they are matrix multiplication, and that is why their GPU is again a better candidate than CPU to compute or to execute all these DNN algorithms, because they also have similarity with the image processing or the video processing algorithm, where each of the pixels are getting processed, or some patch, many of the patches of the image are getting processed together or can be processed in parallel, right. That is why GPUs are heavily used for inference as well as training for training of these DNN algorithms. But then GPUs also have some drawback. The first drawback is GPU has limited memory, right. The highest end GPU has probably 80 GB or maybe around 100 GB of memory. We will see that much memory is actually not enough. Like if we have high end, or if we have like state of the art ML algorithms, we will see that they can easily like take means tens of GBs of memory. The weights itself can take tens of GBs of memory, and then on top of that we have to store activations and all those things, right. For, I mean that is for inference. If we perform training, then we have to store the partial gradients or the partial sums and all those things, correct. So, the main drawback of the GPU is it is limited in terms of memory, right, and that is why these accelerators came into the picture, which are application specific. When we talk about accelerator, it can only execute one specific application. It cannot execute general applications like CPU or GPU can probably execute any general application, but we will, when we will discuss accelerator, you will see that it can execute specific applications. Now, in this context, the accelerators we will discuss, they can only execute DNN algorithms, right. And then on top of that, we will see that they are mostly for inference. Of course, there are some training accelerators, but then most of the accelerators which are getting proposed is for inference, because the idea is we can always train once, we can always use GPU to train the DNN algorithm once, and then use the accelerator for inference, because remember inference is the operation which gets used again and again, right. Let us say in your phone you use Siri or Gemini or whatever. So, internally there can be an accelerator which is performing the computation, or let us not talk about Siri or Gemini. Whenever you have like little high end phone, there is definitely one image processing unit, that is also an accelerator, right. Now, whenever you took an image, then it processes the image very fast, right. Now, I mean that is the role of the accelerator, that is the role of the tiny processor or tiny image processing unit staying in your phone, which processes the image really fast, so that the user experience is good. And again, probably those accelerators or those algorithms are trained once in the GPU, in some GPU, but then once it is trained, you will use that same accelerator or the same algorithm for the entire lifetime of the device, right. So, that is why it is important to have it is important to have inference accelerator for DNN algorithms. Now, whenever we talk about accelerator, we are saying that, okay, I mean as the name suggests, accelerator will just accelerate the application, right. But what are the major performance metric, like how can we quantify that okay, this accelerator is performing good or this accelerator is performing bad. So, there are few performance metrics. The major performance metrics are inference latency, energy, area. So, remember some accelerator can give or can provide like very less inference latency, but then maybe it is using very high end processor. So, it is taking high energy, high area, etcetera. So, it is not worth. So, whenever we talk about accelerator, then all these three metrics should be in check, and at the same time the performance of the accelerator should be much more higher than GPUs and CPUs. Okay. So, I hope it is clear regarding the need of an accelerator. Now, with that context in mind, let us discuss the one of the very first accelerator proposed in the context of DNN, which is DianNao. In Mandarin, DianNao means computer, right. So, as I was saying that this is one of the earliest accelerator for DNN algorithms. Now, at a very high level, the main idea of this accelerator is tiling. So, it uses something called tiling to reduce the memory usage. Okay. Now, again there are multiple types of layers: classifier layer, convolutional layer, pooling layer. So, it uses tiling to reduce the memory usage of all these type of layers. Now, this DianNao or this particular accelerator has an architecture which is tailored for DNN inference. So, for next probably 5 or 6 slides, we will see how the accelerator works. So, we will first see what is the architecture, what is the philosophy, what is the tiling philosophy, and then we will see how this works. Now, just to give you a brief recap, this is the general structure of the DNN, where we have an input. That input is nothing but input feature map. The feature maps goes to convolutional, pooling and classifier layer one after another. There can be series of layers. Some kernels are private, some kernels are not private. Then there are poolings, which is there can be average pooling or max pooling, and then finally there is a classifier layer which is a multi or single layer perceptron. Okay. So, that is the typical general structure of the DNN, which we have discussed in probably 2-3 classes, 2-3 lectures back, right. Now, let us talk about the classifier layer. So, usually classifier layer is nothing but it consists of multi-layer perceptron. Okay. Now, let us say we have one classifier layer where we have 8 neurons in the input and 2 neurons at the output. So, A, J are nothing but the input, and then S, I are nothing but the output, right. So, when we talk about this classifier layer, let us fix some notations. The T in is the number of input neuron, A j is the activation value of jth at jth input neuron. So, you can see that we have 8 input neurons. So, that is why T in equals to 8, and then all these input neurons are denoted by A j. Then we have T out, which is nothing but the number of output neurons. So, in this case T out is 2, and we have W I j. So, remember whenever we have multi-layer perceptron or one layer of perceptron, between 2 layers there are weights, or not the between 2 layers, between the input and output of the layer we have weights, right. So, W I j is nothing but weight from jth input neuron to ith input neuron. For example, if this input neuron is 0 and this input neuron is 1. So, W 01 or W 10 means W 01 means the weight from 0th input neuron to first output neuron, okay. And Si is the sum at ith output neuron, okay. Now, as I told that in this case T in equals to 8 and T out equals to 2. Now, I mean implementing this is of course very simple. We can have a 2 layer nested for loop for I is equal to 0, I less T out, I plus plus, and for j is equal to 0, j less T in, j plus plus, and Si plus equals to A j dot W I j, right. So, S 0 will be nothing but W 0 0, A 0 plus W 10, A 1, and so on and so forth, right. So, that is how both the output will be computed, right. Now, that is a very simple, it is a very simple one layer of perceptron, and this is a very simple implementation, nothing complex in it. But then in this particular case or in this particular computation, let us see what is the number of memory accesses. Okay. So, remember our notation was when we say T in, that is the number of input neuron, A j is the activation value at the jth output input neuron, T out is the number of output neuron, W I j is the weight from jth input neuron to ith output neuron, and then S I is the sum at ith output neuron, right. Now, whenever we say memory accesses, I am repeating this again and again, I know, whenever we compute the DNN, there are different data goes around, right. So, first is weights, we have to fetch the weights from some memory, and then there are activations, we have to store the activations somewhere, and on top of that we have to store the output somewhere, right. So, whenever we have to do some, we have to perform some reading or writing of some data, then memory access come into the picture, right. Again, nothing is free, whenever we perform the computation, whenever we perform some computation, everything takes some latency, everything takes some energy, and all those droplets become like sea of latency or sea of energy. Okay. Now, in this case, let us compute the memory accesses, right. So, the total number of activations is T in multiplied by T out, right, because remember we are performing this A j multiplied by W I j. So, we are computing this T in multiplied by T out number of activations, correct. The total number of weights is again T in multiplied by T out, right, since we have T in number of neurons in the input layer or in input of the layer and T out number of neurons in the output of the layer. So, the total number of weights will be T out, and then finally, the total number of sum, the total number of output is T out, right. Again, all these values has to be stored somewhere, right, some buffer, some memory, somewhere they have to be stored, correct. Now, the total memory access, if we just sum all these components, we will have the total memory access as T in multiplied by T out plus T in multiplied by T out plus T out. So, this plus this is equals to this thing. Now, what is the drawback? So, the major drawback is the number of input neuron can be very large. This T in the classifier layer can be very large, it can be 10 to 1 lakh, right. I mean, if you see the like state of the art DNNs like ResNet or DenseNet, you will see that there are multi-layer perceptron, and at the end of the DNN and then the number of input neurons are very large. Now, the problem is, let us say we have 1 lakh or maybe 100,000 input neuron, right, and then let us say whenever we say input neuron, that means those are the some numbers, right, those are the some inputs, correct, and they have to be stored somewhere. I mean, before computation, if we want to perform this particular computation, they have to be stored somewhere, correct. So, all those 100,000 numbers have to be stored somewhere, and let us say all those numbers, all those activations are 32-bit floating point integer, that means we have 4 byte. So, that means we have, if we have 4 byte for each input neuron and we have 100,000 input neuron, that means we have approximately 400,000 byte, correct. So, 400,000 byte means it is becoming 400 kilobyte, correct. Now, as you can see, I mean, this is just one classifier layer, and that only is taking 400 kilobyte of space, correct. I mean, to just give you a notion, if you just open a Word file and then write few lines, it will be few kilobytes, like 1 kilobyte or 5 kilobytes, right. Now, you can see that just these one classifier layer, just the input neuron can be in the order of hundreds of kilobytes, even it can be in order of megabytes, right, because again remember we are just talking about input neuron, then there are weights and all those things. Now, the problem is our L1 cache, the memory which is sitting nearest to the processor, may not be as big of a size to fit all the input neuron in the L1, right. Now, that is the main drawback, like then how do we do the computation. So, remember, if we want to do some computation, first the data has to be in the L1 cache, and then from that we can put it in the register and then perform the computation. So, that is the usual notion of computation, right. So, we cannot fit in L1, then what should we do? Or rather the question is how to use the L1. I mean, it cannot fit L1, but can we use L1 in such a way that we can still perform the computation? The answer is yes, and the answer is tiling. So, instead of fetching all the input neurons at a time, we can tile or we can divide the input neurons into tiles. So, as I was saying that let us say there are 100,000 neurons, and then if we say that our L1 cache size is maybe only tens of kbs, then we can tile or we can divide the input neurons into tile of such size that it just fits in the tens of kbs of L1 cache, right. Now, this then we will store these tiles in the L1 cache, so that we can go ahead with the computation, right. Now, the thing is that if we do the tiling, so we should not say that okay, we put or we bring some input neurons from the main memory to the L1 cache, and then we do not do all the computation, right. We have to do all the computations with respect to all those input neurons. So, remember whenever we were discussing that code snippet, so we were first computing this T out, right. Sorry, I mean the outer loop was for T out. So, that means we will first compute S0 and then we will compute S1, right. Now, if we use the tiling, we probably cannot do that, correct. So, because if we want to compute S0 first, then probably we have to take some input neurons and then save the partial sum, and then again we have to take the other set of input neuron and then add, right. But that is not what we should do. Whenever we do the tiling, we have to make sure that we are using the tile as long as possible. So, that means we will compute the contribution, and let us say this is one tile, we will contribute the computation of this tile to both S0 and S1, and then we will throw that tile back to DRAM or wherever, and then we will fetch the next tile into the L1, correct. Now, whenever the next tile came, came in the L1, then again we have to compute its contribution to S0 and S1, correct. Now, whenever we computed that contribution to S0 S1, we have to add with the previously computed or previously computed S0 and S1 or the partially computed S0 and S1. So, that is why we need to accumulate the outputs, right. So, now here is a trade off, right. So, of course, the number of times this AI needs to be fetched from main memory is less. I mean earlier for each of the output we were fetching this AI, right, and now for we are not doing that, we are fetching the one tile, fetching a tile once, and then we are performing all the computations which can be done with that tile. So, now the number of times this AI, which is nothing but the input activations, needs to be fetched from main memory is less, definitely, but at the same time the number of times Sj needs to be fetched is more. So, now we have to actually store the partial sums of S0 and S1, right. Then only we can fetch the next tile and then accumulate with the previously computed partial sum. So, earlier what we are doing is we are computing S0 completely, and then we are going to the S1 computation, right. So, right now we cannot do that, we have to compute the partial sum of S0 and then we have to store that partial sum, then again we have to compute the partial sum of S1, we have to store somewhere. So, the number of time Sj needs to be fetched is more. Again, when we go to the next tile, then again we have to fetch the partial sums to finish the computation, right. Now, of course, in this case Sj, the number of output is less. So, we can argue that in this case even if we need to fetch partial sum, it is just we need to fetch just 2 partial sum, it is way lesser than the input neurons, that is true. Now, I mean probably this could have been shown earlier. So, that is the notion of the tile. We have divided the input neurons into 2 tiles and then we are performing the computation corresponding to each tile. Okay. Now, DianNao actually implemented this concept of tiling. So, they implemented the tiling for convolutional layer, where we can tile the input feature map and output feature map. They also implement this tiling for pooling layer. There is no kernel in the pooling layer. So, that is why the tiling does not improve the bandwidth requirement drastically. So, let us discuss this figure. So, as you can see, they are showing the result for they are showing the result of memory bandwidth for classification 1, conv 3, conv 5, pooling 3. So, they are, I think, coming from the Elinet network. Okay. So, when we, as you can see, the first bar is showing the memory bandwidth requirement when there is no tiling. So, this is no tiling case, original. Okay. So, as you can see that this green one is like almost 50% of the memory bandwidth is required for the inputs, correct, and then rest of the 50% is required for the synapses, which is nothing but the weights, right. Now, that means the inputs are getting fetched again and again. So, lot of memory bandwidth is actually spent on the inputs, correct. Now, if we do tiling, then as I already showed you, we can actually reduce the number of times the input is fetched, correct. So, that is why once they perform tiling, you see the green almost vanished. Now, if you look closely, there is a faint of red. Okay. So, if you look closely, there is a faint of red here. So, that is the memory bandwidth requirement for the output. Okay. So, that goes like that was as per expectation, right. Now, furthermore, they also use this L2 cache, where they can use some synapses. So, the memory bandwidth, they can reuse some synapses from the L2 cache. So, the memory bandwidth requirement was reduced further, right. Now, similar result can be seen in convolution layer conv 5 as well as conv 3, where whenever we have this input tiling, then the input bandwidth requirement was less, right. Now, for pooling, there is no concept of synapse. So, there is no blue in pooling, but again, I mean, since the input is tiled, although there is no concept of synapse, but still we are taking the input and then applying the max or average pool, right. So, that is why we when we have pooling, then and then on top of pooling, if we perform the tiling, there is a significant reduction in memory bandwidth required for the input for the input activation. And then again, on top of that, if the L2 cache is used judicially, the memory bandwidth requirement is further reduced. Again, L2 cache is farther from the processor, like L1 is sitting nearest to the processor, L2 is sitting farther from the processor, and typically L2 is shared between different cores. Okay. So, the bottom line is, again, in all these type of computation like tile plus L2, we are not changing the actual calculation, right. The actual calculation is still the same, we will get still the same output, but we are tweaking, we are doing some trick with respect to the systems, with respect to the computer systems in such a way that in this case memory bandwidth requirement is less. Now, if the memory bandwidth requirement is less, that will translate to less latency, and again that is the main motivation of the whole course, that we will never touch or we will barely touch the machine learning algorithm. We will not do anything, any modification in the machine learning algorithm, but rather we will see how to implement this machine learning algorithm systematically or in more efficient way, so that the footprint of hardware footprint like latency, energy, etc., is less. So, that is about the basics of DianNao. In the next class, in the next lecture, we will continue with this DianNao, and then we will see more accelerators. Okay. Thank you.